Renal clearance is an incredibly useful tool for describing various clinically important aspects of kidney function. First of all, what do we mean by renal clearance? The answer to this might seem straightforward, but the concept of renal clearance is actually a little abstract. To understand renal clearance, remember that an important function of the kidneys is to remove various substances from the body in order to maintain body fluid homeostasis. The definition of renal clearance is the theoretical volume of blood plasma that is completely stripped of a particular substance by the kidneys per unit time. So we aren't describing the amount of a substance removed from the body, but rather a theoretical volume of blood plasma. Because we're referring to a theoretical volume of blood plasma cleared of a substance, the units for renal clearance are usually expressed as milliliters per minute or liters per day. The concept of renal clearance arises from the basic anatomical features of the kidney and fundamental conservation principles. Blood enters the kidneys from the renal artery. This represents the primary input for substances into the kidney. Although substances have a single route into the kidney, there are two routes by which a substance can leave the kidney. The first is by the ureter as urinary excretion. This happens due to kidney filtration and/or secretion into the renal tubules. And the second route out of the kidneys is by way of the renal vein. These are the substances that were either not filtered or perhaps they were filtered but then reabsorbed back into circulation. We'll come back to these processes in a moment. So in this example, we have a particular amount of substance X entering the kidney. The amount of substance X is determined in part by the plasma concentration of the substance. If we assume that the kidneys neither produce nor metabolize substance X, then the amount of X leaving the kidneys through the ureter and the renal vein collectively must equal the amount entering the kidneys. You can imagine that the concentration of X in the renal vein is less than the concentration of X in the renal artery. This is because some of the substance entering the kidneys has been excreted into the ureter, thereby diluting the amount of X that's returning to circulation through the renal vein. In contrast, renal clearance assumes that all of substance X that is excreted into the ureter comes entirely from a discrete volume of plasma, such that that fraction of plasma leaving the kidney is entirely devoid of substance X. That is, that fraction of plasma has been completely cleared of substance X. This entails that the remaining unaffected plasma in the renal vein has the same concentration of X as the plasma that's entering through the renal artery. Before introducing the renal clearance equation, let's think about this quantitatively. Say that the concentration of substance X in the renal artery is 1 milligram per milliliter. And let's assume that the amount of X excreted by the kidneys is 10 milligrams per minute. Theoretically, how much of this blood plasma entering the kidneys would be cleared of substance X per minute? The answer is 10 milliliters per minute. That is, under these conditions, the renal clearance of X would be 10 milliliters per minute. In physical terms, this would mean that once every minute, there would be this 10 milliliter fraction of plasma leaving the kidneys that's completely devoid of substance X. Of course, this doesn't actually happen. Instead, the amount of X removed from the blood would be distributed across the entirety of the blood plasma leaving the kidney during that time, manifesting in an overall reduced concentration of X in the renal vein. Okay, so here's the renal clearance equation. The clearance rate of substance X is equal to the urinary concentration of X in milligrams per milliliter times the rate of urine production in milliliters per minute. These terms are divided by the arterial plasma concentration of X in milligrams per milliliter. This gives us the renal clearance of X in milliliters per minute. Note that collectively the numerator is the urinary excretion rate in milligrams per minute. Therefore, this equation computes a rate of urinary excretion normalized to the plasma concentration. Let's apply this equation to our previous example. Again, we assume that the arterial plasma concentration of X to be 1 milligram per milliliter. Furthermore, we assume the rate of urinary excretion of X to be 10 milligrams per minute. This could be achieved with a urinary concentration of X of 10 milligrams per milliliter and a urine production rate of 1 milliliter per minute. This equates to a renal clearance rate of X of 10 milliliters per minute. The renal clearance rates of various substances are highly variable, ranging from negligible values approaching 0 to very large values approaching, say, a liter per minute. What determines the renal clearance rate of a given substance? Ultimately, this depends on how that substance is handled by the kidneys. Let's start with the situation where a substance is freely filtered in the glomerulus. Freely filtered meaning that the substance is not impeded by the glomerular filtration barrier and that the concentration of that substance in the filtrate is approximately equal to the concentration in the blood plasma. So imagine a substance freely filtered, but once filtered, it is neither reabsorbed nor secreted. This means that the amount of the substance that is excreted, its urinary excretion rate, is determined by the amount that is filtered per unit time. The clearance rate of this substance will be some medium or intermediate value. This scenario where the substance is freely filtered and neither reabsorbed nor secreted has additional significance that we'll come back to in a moment. Now let's imagine a scenario where a substance is freely filtered but is subjected to extensive reabsorption mechanisms such that the amount excreted is far less than the amount filtered. An example of this would be glucose, which is extensively reabsorbed in the proximal tubule. In this case, the renal clearance rate would be relatively low. In the case of glucose specifically, the renal clearance rate is essentially zero at normal physiological concentrations of glucose. Conversely, imagine a scenario where a substance is not only freely filtered, but there are extensive secretion mechanisms that move an additional amount of that substance from the peritubular capillaries into the tubular lumen. An example of this would be para-aminohippuric acid, or PAH, an organic anion which is extensively secreted into the proximal tubule. In this case, the amount excreted would be far greater than the amount filtered. Therefore, the renal clearance would be relatively high. So the renal clearance rate can be used to characterize how a substance is being handled by the kidneys. This has important physiological and clinical utilities. Perhaps more importantly, though, the clearance rates of various substances can be used to describe important physiological parameters of kidney function. Specifically, the clearance rates of certain substances can report the glomerular filtration rate, or GFR, which is the volume of fluid filtered by the kidneys per unit time, and the clearance rates of other substances can report the renal plasma flow, RPF, or the volume of blood plasma perfusing the kidneys per unit time. In order to understand this, let's go back to the scenario where a substance is freely filtered and neither reabsorbed nor secreted. This is where the amount of the substance that's excreted is equal to the amount that's filtered. Let's formalize this a bit more. The amount that is filtered per unit time is called the filtered load, usually expressed in milligrams per minute. The filtered load of substance X is the product of the plasma concentration of X and the GFR. Remember, when a substance is freely filtered and neither reabsorbed nor secreted, that means that the amount filtered, that filtered load, is equal to the urinary excretion rate. If we rearrange this expression and solve for GFR, we can see that GFR is equal to the renal clearance of substance X. Note, this is only true if substance X is freely filtered and neither reabsorbed nor secreted, such that the filtered load equals the urinary rate of excretion. So what are examples of substances that fit these criteria? The two most commonly described substances are inulin, a plant polysaccharide, and creatinine, a metabolite of muscle creatine. This means that if you measure the renal clearance rates of either of these two substances, or any substance that is freely filtered and neither reabsorbed nor secreted, their renal clearance rate is the GFR, that is, the volume of fluid that's filtered by the kidneys per unit time. Pretty cool. But wait, there's more. Some substances are not only filtered, but are so extensively secreted that nearly all of the substance is removed from the blood plasma on a single pass through the kidneys, such that the substance is virtually absent in the blood leaving the kidneys through the renal vein. An example of this is PAH. Note that this is only true at low plasma concentrations of PAH. In this case, the renal clearance of that substance, again, let's say PAH, is not only very high, it is equal to the renal plasma flow. This is because the amount of PAH that is excreted by the kidneys is equal to the amount that's entering the kidneys. How much PAH is entering the kidneys? This is the product of the renal plasma flow and the plasma concentration of PAH. Again, rearrange and solve for RPF, and it should be apparent that the renal plasma flow is equal to the renal clearance rate of PAH. But again, only because PAH is filtered and extensively secreted by the kidneys. So there you have it. This was just a quick introduction of the renal clearance equation and a brief tour of some of the important applications of renal clearance rates. In subsequent videos, I'll go into further detail of how renal clearance rates can provide additional insights into kidney function and how the parameters determining renal clearance can be altered by kidney injury or failure.